So 8.6 is alternating series. So what does an alternating series mean? What are they talking about? The alternating refers to the sign of the numbers. So an alternating series is going to be a series in which the sign of the numbers alternates. So you have a positive, then a negative, then a positive, then a negative, or vice versa. And so what we might want to recognize is that before now, all of our series and all of our work with series has been series that were only positive in their terms, so that every term was a non-negative number. In fact, all of our theorems about that also applied only to series that had positive terms. So what happens with our work with series if now the terms of the series might alternate in sign? So in order to think about this and begin to consider this with an example, we're going to focus on the harmonic series. So again, let's remind ourselves, the harmonic series is this crucial series, which is the series as k goes from 1 to infinity of 1 over k, or 1 plus 1/2 plus 1/3, etc. And so reminder, we even have a theorem of this. This series diverges. And we can now easily see that this series diverges with multiple versions of our tests. For example, this diverges by the p-series test. You could see that, anyway, so it's easy to see that this diverges with our work. We did it at the time by looking at it numerically, graphically, and even analytically. I kind of showed that you could just keep adding a half, getting something that's more than a half that you just add endlessly as many times as you want, that causes the series to diverge. So how would this, well, first of all, this is a crucial series because if you consider it, for example, in the p-series, this is the very first value of p, namely where p is a 1, the power on the k is a 1. This is the very first value that causes the series to diverge. And I looked at this a little bit back when we did improper integrals. The integral test for the p-series, for the harmonic series would also show that it diverges. But in particular, when we were looking at improper integrals, I said that the 1 over x function was a crucial function because it's right on the edge of divergence versus convergence. So in this case, this basically, as soon as I make the power on the k anything more than a 1, like 1.00001, then all of a sudden the series goes from diverging to converging. So this seems to be a very crucial series. So now let's consider the alternating harmonic series. So what would that look like? So first of all, I'm going to write the notation for it. So I'm going to have this summation as k goes from 1 to infinity, and I know I have 1 over k here. So how do I make that alternate in sign? The way we make it alternate in sign is usually by putting in a -1 to the power k. Because if you put -1 and raise that to the power k, then every time k is an odd number, -1 will give you negative. And every time k is an even number, the -1 will give you a positive. So that way you can alternate from positive to negative just because the values of k alternate from being odd to even. So what I'm going to do is instead of just a 1 on the top, I'm going to put a minus on the 1, and then I'm going to put a power on it. So if I put k as my power, then the first term would be, k being a 1, would be -1 to the 1 power over 1, which would be -1. Then the second term would be -1 squared, which is +1, over 2, which would be +1/2. So if I do this as it is written now, then what I'll get is -1, +1/2, -1/3, +1/4, etc. So, however, I'm going to, for consistency with the book, and because this is what we normally like for the alternating harmonic series, I'd like this to start with a +1 and then switch to a -2. So how can I make all of these basically the opposite in sign of what they were? So what I want to do here instead is I want it to, on the odd powers, be positive, and on the even powers be negative. So I just add 1 to my power up here. So I'm going to put a little +1 on my power of k. So now when k is a 1, the -1 is squared and becomes a +1. When k is a 2, then my power is a 3, and -1 to an odd power of 3 becomes a -1, etc. So this will start now with a +1, and then have a -1/2, and then have a +1/3, and a -1/4, etc. So this is called the alternating harmonic series because it has the same numbers as in the positive harmonic series, except they alternate in sign. And we've chosen it to start with the first number being positive and then switching to negative, positive after that. So this is called the alternating harmonic series. Okay, so any questions about what the alternating harmonic series is, or about how we've chose to write it? Okay, so this is a modified version of the harmonic series, and we know the harmonic series diverges. So as with any new series that we're looking at, like this alternating harmonic series, our question always is C or D. Does this converge or does this diverge? Maybe it diverges like the original harmonic series, or maybe now that we've changed it, maybe now it converges because it is different than the one we started with. Okay, so, well, the first thing to point out is that all of our tests do not apply here, with the exception of the divergence test. But basically, we don't have an ability, we can't use the ratio test or the integral test or things like that, because those all had built into their setup that they assumed that the series you were talking about was positive terms only. So like we did with the first look at the harmonic series, our first look for the alternating harmonic series, we're going to start numerically, graphically, and analytically. And also, like before, the book does a nice job of doing this numerically and graphically. So I'm going to give you an analytical argument to draw a conclusion. So basically meaning I'm going to just do some analysis of what we have here. So I'm going to have us consider this series two ways. Consider this new series two ways. So first, we can see that that you could imagine if you were doing your partial sums, that we could look at the even numbers in the partial sums as follows. So S sub 2 would be the second term in the partial sum where we added up the first terms, and that would be 1/2, because that would be 1 plus -1/2. then S sub 4, so that, if we think of S sub 4, that's the sum of the first 4 terms. And if you have a finite number of terms, you can add them up in any order. So imagine that I'm adding up these two and these two. So that would give me 1/2 for the first 2. And then on the next 2, I would have 1/3 minus 1/4, which is 4/12 minus 3/12, leaving you 1/12. So then if I add 1/2 and a 1/12, that's 6/12 plus 1/12 is 7/12. So then what happens, for example, if I go up to S sub 6? So I'm not going to actually try to get this exact value, but what I'm going to argue is that then you would be adding the next 2 terms, and we're not even going to worry about what they are at this point. But if I'm doing 2 terms at a time like this, remember, as in the regular harmonic series, the denominator is growing by 1 each time. So that means the size of the number is getting smaller and smaller. So for each one of these pairs, because I started with a positive and I'm going 2 at a time, I have a positive number plus a negative number. Then I have a positive number plus a negative number, and that would happen again. I'd have a positive number plus a negative number. But because the negative number in my pair is second to the positive number, it's smaller in size. So the pair of numbers that I'm adding when I go to the next even partial sum will always add some additional positive value to what I had up till that point. So for example, S sub 4 was 1/2 plus an additional 1/12. Because the new pair of numbers I added an extra 1/12 in value. Then S sub 6 will be 7/16 plus some small amount, because the resulting amount additional for the next 2 numbers will be the sum of a positive and a negative number, where the negative number was smaller in size than the positive number. In this case, it would be 1/5 is a larger sized number than negative 1/6, even if you look at their absolute value. And so that means that I would have 1/7/16 plus some positive amount. So what we can see if we look at the even partial sums is that you get a value that is increasing each time. It never decreases because you're always adding some small additional positive amount. So what I conclude from this is that the even partial sums are monotonic and increasing. So that means if we don't necessarily, if we looked at every term of the partial sums, it would not be monotonic nor increasing, because it would go up and then down and then up and then down and then up and then down a little bit at a time, because the signs of the numbers are alternating. But we can kind of look at the end result of where they're heading, because the sequence of partial sums, if we just look at the even numbers, they form a monotonically increasing value. So that means, for example, that the overall sum of the series could never have a limit of some negative number. If it has a limit at all, and it might be that it just diverges, but if it has a limit at all, it couldn't be a negative number, because if you look at every other term in the sequence of partial sums, they form a monotonically increasing sequence. So there's a lot of math in there that may be confusing, but nonetheless, hopefully this gets an idea. Let me take away some of this scratch work so that we can look at the next phase of this. Okay, so then now let's consider this a slightly different way. We're going to do the same thing, but we're going to look at the odd the odd partial sums, basically. So let's look at S sub 1. So S sub 1 is just the first term, which is 1. And then S sub 3. So S sub 3, I'm going to have us consider sort of in a similar to the way we consider the even ones. To get from the first partial sum to the third partial sum, we are adding 2 more numbers, namely these 2 here. We're adding 3 terms up, and we added only the first one in the first partial sum, so we're adding 2 more terms. So how do they contribute to the total we had up to this point? Well, then you're going to have a negative number plus a positive number, where now the positive number is smaller in size because it follows the negative number. In the case of these 2 here, if I have negative 1/2 and positive 1/3, I'm left with negative 1/6. So that means that the third term is 1 minus 1/6, which is 5/6. If I look at S sub 3, then I'm sorry, S sub 5. So as we try to sort of see a pattern here. So then when I go to the 5th term, I would add 2 more numbers, negative 1/4 plus positive 1/5. But the pattern to see here is that you add a little negative number here. And the negative number is decreasing in size. So the negative number is going to be, well, let's go ahead and just do it out in this case. So I have 1/4 and 1/5, which has a common denominator of 20. So this is negative, let's do that here. So this ends up being negative 1/20. And so I have the number that I had before, 5/6, but I'm now subtracting a 20th. So let's see, I guess I will go to 60ths. So that's 50/60ths minus 3/60ths is something like 47/60ths. Doing that in my head, hopefully that's right, something like that. So basically what we can see is that if I look at these values, I have a monotonically decreasing sequence. So the odd partial sums monotonic decreasing sequence. Questions so far about this logic or this idea? I know it's a little thick.
Can you explain how we got the even and the odd terms again, really quickly?
Yeah, so again, these are partial sums. So a partial sums mean you add up the terms of the sequence up to this point. So I basically said, well, S sub 2 would be the sum of the first 2 terms. So we add up 1 minus 1/2, 1 and minus 1/2. Then S sub 4 means you add up the first 4 terms, meaning 1, negative 1/2, positive 1/3, negative 1/4. So I just did the arithmetic. But then while doing the arithmetic in the early stages, I asked us to try to recognize a pattern that would hold throughout the entire sequence of the even numbered partial sums, in that each time you add two more numbers from the sequence to the partial sum to go from a 4 to a 6 or to an 8 or whatever, that the new pair of numbers you're adding would contain a positive number and a negative number, where their sum for those two would be a little positive number. So that every time I advance to the next partial sequence terms, I'm always getting a little added positive number value to the total I had up till that point. Does that make sense?
Yeah, it does.
Okay. So what we're seeing here is that if you look at these two ways of looking at the total of the partial sums along the way, that if you look at every even partial sum, you start with a half and you keep getting bigger and bigger and bigger and bigger. If you look at the partial sums from the bottom, then if you start it if you look at the partial sums that are odd numbers, 1, 3, 5, that you start with a 1, but then you get smaller and smaller and smaller and smaller because you keep subtracting a little bit. And the sizes of the numbers that we're talking about are heading down to 0 very, very quickly. And so what we basically have is we have a sequence of numbers which are bound above by 1, because they start at a 1 and go down if you look at the odd partial sums, but they're bound below by 1/2, because after dipping down to 1/2 on the second partial sum, it just keeps increasing from that point forward. So the values are all trapped between a 1 and a 1/2, and these individual examinations of the partial sums with the odds and the evens, meaning that each of these must converge to a value. So think of it this way. The even partial sums are bound above by a 1 and below by a 1/2, and the even ones are monotonic and increasing. So if they're monotonic and increasing, they converge. Because we had a theorem that told us that any monotonic bound sequence converges. And the odd partial sums also are bound. They're bound above by a 1 because and below by a 1/2. And they are monotonically decreasing if you consider them separately. So they must also converge. Well, since these are part of the same sequence, just sort of separated into the odd ones versus the even ones, then they're both converging, and the values that you're adding each time are getting smaller and smaller. So therefore, the harmonic series, the alternating harmonic series converges to some number. It's terrible.
I have a question in terms of what each is bounded by. So for the even partial sums,
Yes.
Is that only bound by 1 and 1/2?
Well, it only needs to be bound by one number. The size of the numbers only need to be bound by one number, but they're bound below by 1/2. They start with a 1/2 and they're getting bigger and bigger and bigger and bigger, but they're bound above by a 1. Because the grand total of the partial sums can also be seen as starting at a 1 and getting smaller and smaller and smaller.
Okay, thank you.
So we're not actually even at this point going to try to say what it is that they become. We are just wanting to recognize that the conclusion that they converge. If you look at, they explore this numerically and graphically in the book a little bit. And if you look in the book, it looks like it's something around 0.7, something like halfway between the two, maybe 7, anyway, something halfway between like 0.5 and 1. Maybe it's halfway or very close to halfway. It just looks like it's something around 0.7 if you look at it numerically. but we know that it's bound above by 1 and it's bound below by 1/2. And so since the odd and the even partial sums both converge to a value and they're part of the same sequence, they must converge to the same value. Other questions about this idea? Oh, I'm not able to see. Let's see this. So Marcus says, does the limit not exist? That might have been an older question. I didn't have my chat box up. You talking about the alternating series here, Marcus? Anyway, okay, so what does this mean for us? Well, the thing to take note of this is that we have a series where we've been able to look at it two ways, both when it was alternating and also before when it was not alternating, when it was just all positive. And so by taking the exact same series and allowing every other term to change sign, it's possible to have a divergent series become a convergent series. And you can think of it this way. What does the idea of convergence and divergence mean for series? The basic idea is we're trying to see, does the sum as we're going out and out and out settle in on a value? And one of the most common ways that it might not settle in on a value is because it goes off to infinity. If all the terms are positive, then the only way that it can diverge is to go off to infinity. Because if all the terms are positive, you can never decrease in value, you can only increase. You have to be non-decreasing if all your terms are non-negative. And if you're bound above, then you must converge. We have a theorem that tells us if you're monotonic and bound, then you have to converge. So when you only have positive terms, the only way you can diverge is by going to infinity. So the thing to recognize is if I then make the terms alternate in sign, then it's going to be a lower result, even with the partial sums, than if they were all positive. If they're all positive, they're all causing the sum to increase. By making them alternate between positives and negatives, well, then it will simply increase less than it would have if they had all been positive. And by making them increase less, it's possible that you take a divergent series that would have accumulated off toward infinity and all of a sudden have it converge on a number. And the harmonic series is the quintessential example of that. So the harmonic series, if you leave it with just positive numbers, 1/2, 1/3, 1/4, 1/5, 1/6, that accumulates to values larger than any number you can think of. That heads off toward infinity. But if you cause those numbers to alternate, then as we've just been considering, actually it then converges to a number less than 1. So with an alternating series, it's possible that in its alternating form, it converges, but if it wasn't alternating and all the terms were just positive or all just negative, that possibly then it would diverge. Questions, comments, discussions about that? Okay, so I think I want to introduce some vocabulary here. No, that comes a couple of pages later. So I'll try to stick to the same order that's going on in the book. All right, so this means we're going to look at, we're going to introduce a theorem. So this is theorem 818. on page 650. So it's called the alternating series test. We have another test. But now that we have a new kind of series where the terms alternate, it's good to introduce a test for that kind of series. So if you are looking at a series and you're trying to evaluate whether it converges or diverges, if it's alternating, this is the first place you turn, to the alternating series test. Because remember, a lot of our other tests all were based on the idea that the series had only positive terms. So we need a test for our alternating series. So it says the alternating series and we're going to write the alternating series with a summation notation, k going from 1 to infinity. But what we're going to do is we're going to assume that it starts with a negative number. We could always factor a negative out of every term of the series if it didn't, and multiply -1 times one that did begin with a positive. And we're going to put in front a -1 to the k plus 1. So that's going to make the signs alternate, and then we're going to put a sub k. So when we do this, notice we are causing the signs to alternate with the -1 with the power on it. And so the a sub k's themselves will always be positive, because we're taking care of the sign of the alternating series with this expression out front. So the expression for a sub k for an alternating series will be an expression that does not itself alternate, but then when you add the -1 to the k plus 1 power out in front of it, that causes the series itself to alternate in sign. So we're going to say the alternating series written this way converges provided two things. One, needs to have two things for this test to tell us that the alternating series converges. So the first one says the a sub k terms are non-increasing. Again, vocabulary from before. And they use the word in magnitude. But again, we've already set this up so that these are sort of positive numbers. And number two, the limit as k tends to infinity of the a sub k's is equal to 0. Okay, so do we remember what non-increasing means? Let's maybe remind ourselves of that, because maybe that was forgotten a couple sections ago. So the a sub k's are non-increasing, which means that a sub k plus 1 is less than or equal to a sub k. So that means that they don't oscillate in size. They don't get bigger and then smaller and then bigger than smaller than bigger than smaller. They strictly just get smaller or stay the same in size. And eventually, the limit goes to 0. That if those two things are in place, then an alternating series must converge. And so I'm just going to add to this real quick, and then we'll apply this test a couple of times to get used to it. But I'm also going to point out that the conclusion that we drew in our first example, they formally do for theorem 819. In theorem 819, they conclude the alternating harmonic series converges. Even though the regular harmonic series diverges. So this sort of fact is kind of crucial, so that's why they even pointed out in a theorem. Like before, we had a theorem that told us that the harmonic series diverged. Okay, so looking at this first example, we can see that when you take a series with only positive terms, but then all of a sudden make a new series out of it by having the terms alternate in sign, that you can literally take a series that diverged and went off to infinity and turn it into a series that converges to a number. And we now have a test that's for alternating series. And notice the requirements of the test for the alternating series are met by the normal harmonic series, except for the fact that it's not alternating. So for example, in the normal harmonic series, the terms are non-increasing. They just keep, in fact, they're strictly monotonically decreasing, and they go to 0. So both conditions 1 and 2 are met by the normal harmonic series, but it diverges, but only because it's an alternating series does it then converge. And basically they're saying this is true for any alternating series, that if the terms are non-decreasing and go to 0 and it's alternating, then that is a convergent series. So notice that these conditions in the alternating series test are weaker than the normal type of test conditions that we have, because they could actually apply to a divergent series that wasn't alternating. And then when you add the condition of it being alternating to these two conditions, then all of a sudden it makes it converge. So what this means is that it's basically easier for an alternating series to converge because it's alternating than if it wasn't alternating. Questions, comments, discussions about that before we just look at an example of using the test? All right, so again, just to be clear, this is a test for convergence of an alternating series. It does not say that if they don't meet these conditions, that it must therefore diverge. It doesn't say that. Okay. Now, I will point out that we would think that if the limit of the k terms did not go to 0, then that itself would sort of make you think that it has to diverge. At least it sounds like it from the divergence test. So let's take a look at that. So if I look at a reminder from theorem 8.8, the divergence test says that if a series converges, then the terms go to 0. Equivalently, if the terms do not go to 0, then the series diverges. So if this test here, the alternating series test, if this part was not satisfied, if the terms did not go to 0, then the divergence test would give you that it diverged. So if not true, then divergent. So the only way we could sort of have this test fail is if you had something where and not know that it's divergent, is if you had something where this second part we didn't know goes to 0. It does go to 0, but the first part, they weren't strictly non-decreasing. All right, I'm getting a little bit in the weeds here. Let's just look at an example. Okay, so let's try maybe look at example 1 for this section, which is on page 652. Let's just do the first one. Start simple here. So it has the summation as k goes from 1 to infinity of -1 to the k plus 1 power over k squared. So because of this -1 part up here, that's how we can see that this is an alternating series. And in particular, if that wasn't there, then we could see that this would just be 1 over k squared. So basically, this is the alternating version of the 1 over k squared series. So does anybody know if the non-alternating version, the 1 over k squared, does that one converge or diverge? Does anybody know? Question for the group. Does the series of 1 over k squared converge or diverge?
Converge.
It does converge, and what's the justification for that?
The P series.
P series.
Perfect. So I'm going to say which converges. So here we have a series that was already convergent, and then we made it into an alternating version. So what would we think is going to happen with the alternating version of 1 over k squared?
Would it diverge?
Well, what we were saying is by taking a series which diverges when they're all positive and making it alternating, it made it more possible that it would converge. So if it already converges and then you make the signs alternate, do you think that would give you a bigger total? Do you think you'd get a number that then runs away to infinity by making every other term be the opposite in sign?
No, it would be smaller, so it would be the same thing, right? It would converge.
Yeah, so the thing I'm trying to, and this is exactly why I'm asking about this, because the thing we want to recognize about what happens when you take a series and make it alternating is that it only increases the likelihood of convergence. It never decreases it. It only makes it more likely that it will settle on a value, because it's hard to run away and accumulate a value if you are changing the sign of what you're adding every time, because you get cancellation between pairs of terms, and so you end up adding less and less and less. But anyway, we can still test this. So how would I test it? So the first thing for the alternating series test is to say that the a sub k part without the alternating sign is non-increasing. So first we would note 1 over k. Let's do notation a little different. So a sub k is equal to 1 over k squared. And that's non-increasing. Because as k gets bigger, the value of the fraction only gets smaller. And 2, the limit as k goes to infinity of 1 over k squared equals 0. Therefore, by the alternating series test, the series converges. So, questions about that?
I have a question.
Yes.
So how did you know that you can rewrite like the -1 to the k plus 1 and say it's 1 over k squared?
Oh, so this is not supposed to be equal to that whole thing. So
okay.
the whole thing we're thinking of as -1 to the k plus 1 times some a sub k. So that we were basically considering the alternating part separately. And that notation was introduced in the alternating test. So to use the test, so let's go back up to the language of the test. So here's in the alternating series test, here's the notation, right? And what it's basically saying here is this is the part that causes the alternating, and then a sub k is the part that comes after the -1 that's alternating. And that then when we discuss a sub k in parts 1 and 2, we're not talking about the -1 part. We're only talking about the part after the -1.
Okay.
Can you see that?
Yeah, that makes sense.
And so then when I got down to this specific example, I'm pointing out what a sub k is because it's not the same as the whole thing, because it doesn't include the -1 with a power on it when I'm trying to apply the test. And so because I'm doing my 1 and 2 here from the alternating series test, I'm then applying the notation from the test, which says look at the a sub k part that came after the -1 to a power, and then determine if that's non-increasing and if it goes to 0.
Okay, yeah, that makes more sense now. Thank you.
Yeah. Okay, great question. Other questions at all about this example of using the alternating series test for convergence? All right, so let's give you guys a chance to try one. Let's see. So I'm going to try doing some erasing so I can keep this stuff here. I'm going to erase this theorem about the divergence of the harmonic alternating series. We'll clear this page when we go to a new topic in a minute. So let's give you guys one to try and use the alternating series test and see if it allows you to draw a conclusion about convergence. And let's see if I can get the test on the board. Okay, so here's the test. And now let's try example 1b, but I'm going to put it up here and then give you guys a couple minutes to give it a try. So again, it says determine whether the following series converge or diverge. And in B, the series is 2 minus 3 halves plus 4 thirds minus 5 fourths plus dot, dot, dot.
Would it diverge?
So that seems like a possibility. What makes you think that it might diverge?
I'll just explain what it. So I just looked for like the pattern that was going on for a sub k.
Mm-hmm.
I got a sub k equals k plus 1 over k. Because that's just a trend that I saw, and then I simplified that to 1 plus 1 over k. And then when you take the limit, you just get 1. So you can't really use the alternating series test. Like it doesn't.
Part two.
Right? Yeah, part 2.
And as I circled in blue here, if part 2 is not true, then it diverges by the divergence test. So the divergence test was one of our earliest tests. It was our first test, and it actually didn't specify that it had to be positive terms. It simply said, if the terms don't go to 0, it diverges. So Cielo, you're exactly correct that because the terms don't go to 0, this diverges, alternating or not. Now let's look a little bit about what you were saying in terms of notationally. So here's what she observed. She observed that the top number in each of these fractions is 1 more than the number on the bottom. 5 over 4, 4 over 3, 3 over 2, and the first one is really a 2 over 1. So that means that we can write this as the summation as k goes from 1 to infinity. Now to make it alternate, I'm going to put a -1 to the k plus 1 power. That's going to make it start with a positive term and alternate in sign. But then after that, you have k plus 1 over k. And so in this notation, this part causes it to alternate. And this part we're going to call our a sub k part, meaning the part that's not causing it to alternate, but is a formula. So then we can see that the limit as k tends to infinity of k plus 1 over k. And there's lots of ways we can do this, L'Hopital's rule, and algebraic manipulation, but you get a 1. And that's not 0. Therefore, this diverges by the divergence test. So that's correct conclusion, Cielo, as well as the perfect logic that got you there as well. Questions, comments, discussions about that?
How did we end up getting that equation?
The k plus 1 over k?
Yeah.
So yeah, that's challenging. So this goes back to when we very first introduced sequences and talked about trying to recognize a pattern. So it's like, I don't really know what to say, because there's definitely pattern recognition is not something we can tell you exactly how to do that or how to see that every time. And it is a key part when you're just looking at a list of numbers of trying to figure out what's going on. And the truth is, normally this would be investigated and practiced a little bit more thoroughly in a better introduction to sequences and series than we had here. So for example, typically in like a pre-calculus class, we'll do a lot more examples like this. And in a pre-calculus class, we'll not only introduce a geometric series, but we'll also introduce an arithmetic series, which is one where you're adding the same number every time. And we kind of just had to go a little bit more quickly over that, and we even ignored an arithmetic sequence or series because that's not what we're focusing on in calculus. But in the heart of all of that stuff is this idea of pattern recognition and looking at how you could predict what the terms are with a formula. And all I can say is that she correctly observed that in every number, the number on the top of the fraction was 1 more than the number on the bottom in order to come up with that formula. So you can kind of see what was observed this time, but I can't give you sort of a step-by-step process to come up with the formula every time in general for pattern recognition, because any particular pattern could be different. It's kind of like word problems, the more of them you do, the more comfortable you get. And hopefully they won't ever give us examples much more challenging than this one or like this one. But unfortunately, I can't give you a, ABC step process of how to come up with formula patterns. So I recognize my own answer as being a little unsatisfying, but I don't know what to say other than that. Other questions about this example at all? Okay, so we are in a similar position to what we were into a little bit before, in which they talk a little bit with one example about how to come up with the remainder in an alternating series, which we talked about before for other series, meaning it's sort of a formulaic way to try to narrow in approximations. And as I mentioned before, the more standard way to do that is just using technology and digitally. And so I'm going to gloss over that and focus instead on the very next page on a new definition and our last theorem for the section to finish up the section. And then after that, we'll take a break. So let me go up to the top here and clear the page. And so then on page 654, I have a definition. And it's for absolute and conditional convergence. Okay, so let's just write out and then we can discuss it a little bit. It says if the absolute value, well, one step ahead of myself, if the series of the absolute value of a sub k's converges, then if I take away the absolute value on the series, then we write then the series of a sub k's converges absolutely. Whereas if the series of the absolute value of a sub k's diverges, and the series of the a sub k's converges, then we say that the series of the a sub k's converges conditionally. So what we're defining here are absolute convergence and conditional convergence. And so what's the difference is in our expressions here is we have a series where you make all of the values of the series positive because you put absolute value on it. And you're comparing that to if you did not make them all positive and you just have a sub k's. So an example might be that if you had an alternating series where every other sign was negative and you slap absolute values on all the terms, then it's not alternating anymore. And then all of a sudden it's a series with only positive terms instead of alternating. And so we can, for example, consider, well, we can do an example below. So what this basically says is if when all the terms are positive, the series converges. Well, as we've discussed before, if you then make some of the terms negative, you increase the likelihood of convergence. So if it converged before any of the signs were negative, then when the signs are negative, we say it converges absolutely, meaning that even if you put them in absolute value, it would still converge. So let me put a little example next to it that we've already looked at. So an example would be the series of -1 to the k plus 1, so it alternates, divided by k squared. So we looked at this. Oh, that looks terrible. Let me just rewrite that. Sorry. So let's just do this better. An example, just to put it next to the term. The series of -1 to the k plus 1 divided by k squared. So we looked at this already in one of our examples. And what we observed is that, well, if the -1 weren't there to make it alternate, this is just 1 over k squared. And then all the terms would be positive if we didn't have the -1 alternating there. And then that would already converge by the p-series test. So this is a case where if I put absolute values on it, the -1s would just go away and I would just get a series that I know converges. So I'm going to say that that converges absolutely. Oops. Yes, I know. Schools are closed. All right, so this is an example of a series that converges absolutely because without the -1s on there, it would still converge. And with the -1s on there, it definitely converges. So we say it converges absolutely. Whereas in the next example, it says that if you put absolute values on the series terms, making them all positive, it diverges, but that if you don't do that and you consider the series by the self, it converges. Then we say that converges conditionally because its convergence is conditional on the fact that the signs have some negatives. And if they didn't, it would diverge. So that's why it converges conditionally. And so our perfect example of that is the alternating harmonic series. So that would be if I made it alternate with the k plus 1 on it, but I just put it over k. Well, here, if I put absolute value on and made the -1s go away, I would get the harmonic series, which we know diverges. But when you put the -1s on there and then allow it to alternate, then it all of a sudden converges. So the changing of the signs changes it from divergent into convergent. So we call that a series that converges conditionally. So questions at all about that definition and examples that it applies to? All right, so the next theorem is going to be something that we basically rely on for all of our work with alternating series tests, or almost all of it. And that's the basic idea that if the -1s, or if some negatives are added somewhere in along the way, that will only increase the likelihood of convergence. So that there are some series which are conditionally convergent, and you need the help of some minuses to make them converge. But certainly, if they converge without the addition of some minuses, then it would definitely converge when you put some minuses in. And that's the next theorem, states that. So let's look at this. So then a couple inches below this definition, again on page 654, we have theorem 821. Still on page 654, which states that absolute convergence, meaning you take away all the minuses and you get convergence, implies convergence. So if you have any series that is not always positive terms, and it may have some negative signs sometime, or it may be that they literally alternate and that it's an alternating series. But if you have any series where sometimes there's minuses, and you apply absolute value to it to get rid of all the minuses and make them all positive, and you still get convergence when you do that, that means the more complicated series with the minuses converges as well. That by adding some minuses sometimes, you cannot turn a convergent series into a divergent series. So let's write this up a little bit more formally. If the series of absolute values of a sub k converges, then the series, of the a sub k's without the absolute values converges. Questions about that? All right, so let's look at an example. Example 3 on page 655. And we'll look at A. And again, it says determine whether the following series diverge, converge, and specifically if they converge absolutely or converge conditionally, to try to help you use this new definition. So our first one is the series k goes from 1 to infinity, -1 to the k plus 1. So that makes it alternate. And then we have that divided over square root of k. Okay, so we want to figure out if it converges or if it diverges. And if it converges, we want to figure out if that's conditionally or if that's absolute, meaning that it didn't matter if the -1 is there. So, first of all, if it converged without the minuses, then it converges absolutely. And I know that the series converges itself by the theorem we just looked at. So we begin, I'm going to say we start by considering the series of the absolute value of a sub k's. And if that converges, that means the series itself converges, and specifically that it converges absolutely. So we'll start with that. Now, if this diverges, it's still possible that the original series converges, because it might be that it conditionally converges, or it might be that it diverges as well. Okay, so we start by considering this. So that would lead us to consider the series of 1 over the square root of k. Because if I put absolute values on the terms, it's just going to cause the possible -1 on the top to always just be a positive one, and I get this. So looking at 1 over the square root of k, does anybody have an opinion about whether that converges or diverges?
Converges because of the p series.
That's the perfect series to quote, but the wrong conclusion. So you're recognizing the square root could be a power, so we would use the power series, right? What power would a square root be?
1/2.
Yeah, so the p series says if the power is less than or equal to 1, it diverges. And if the power is bigger than 1, then it converges. So you're right, you should see this as a power series and use the p series test. but then the p-series test should tell us that this diverges because the power is less than 1. Does that make sense, Prajit?
Yeah, I just thought it was the other way around.
Yeah, yeah. And so remember, the counterexample to this, which we just looked at a bit ago, was 1 over k squared. So the simplest examples of the p-series going in one direction or the other to help you keep the two clear is that 1 over k squared converges and 1 over k to the 1/2 diverges. Is that okay?
Yeah, that makes sense.
Okay, so we say this diverges by p-series test with p equal to 1/2, which is less than 1. I don't like that 1/2. Okay, so what does this tell us? This tells us that when I take this alternating series and I slap absolute values on it, it diverges. So that may mean one of two things. It may mean that the original series also diverges, but it may also be, like with the harmonic series, that when you make it alternating, it goes from being divergent to convergent. And if that's the case, then we would label this as conditionally convergent. So how do we figure that out? Well, now we can't say that the absolute value converges, so we can't use that to get that this converges. So then we have to use the alternating series test. So we started by considering the series of the absolute value. So now try the alternating series test, because we still don't know whether the original series converges, but it is alternating. Okay, so step 1, does the a sub k's, again without absolute value, if we set the a sub k's equal to just 1 over the square root of k, does this sequence only decrease? Is it non-increasing? So the first condition of the alternating series test is that the terms are non-increasing. So what do you guys think? Do these terms just decrease, 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 or do they sometimes decrease, then increase, or go back and forth? As k gets bigger here, what happens? Anybody have an idea?
Wouldn't it get smaller?
It would get smaller because the denominator, even if it has a square root on it, as the denominator gets larger and larger, the fraction will get smaller and smaller. So does this only decrease? The answer is yes. Increasing k causes the fraction to decrease. And k only gets bigger when you go 1, 2, 3, 4, 5, 6, 7, 8, 9. So then in part 2, we have to take the limit as k goes to infinity of this term. And what do we think we get here?
Wouldn't that be approaching 0 eventually?
Yes, sir. And again, this goes kind of back with our limit comfort from chapter 2, but we did have a specific thing in sequences that this not sequences, but that when you have a power in the bottom of a fraction that's just making the number bigger and bigger, that the overall fraction goes to 0. So we have an alternating series. that is non-increasing and the limit of the terms equals 0. So therefore, by the alternating series test, it converges. And to finish the problem, since the series given converges, but the series of absolute values of k diverges, we say the series converges conditionally. Oh, it's conditionally convergent. Let me reorder those words. Not that that's crucial, but is conditionally convergent.